In the previous lectures, we discussed the Laplace transform and the properties of Laplace transform, and now in this presentation, we are going to discuss the inverse Laplace transform. So, let's get started. In the part 1 of the review of Laplace transform, we discussed that the inverse Laplace transform is the method to find out the time domain function whenever we are given the frequency domain function. We also discussed the expression to find out the inverse Laplace transform, but we are not going to use that complicated expression in order to calculate the inverse Laplace transforms. Instead, we are going to use the method of partial fractions and some properties of Laplace transform. And we will understand these things with the help of some examples. And the example number 1 is given as: find the inverse Laplace transform of f of s is equal to 1 over s plus 3 whole square. Now in this case, we are given a frequency domain function and we need to find out the respective time domain function by the use of inverse Laplace transform. So if we observe this function, then this particular function is looking like a frequency shifted version of 1 over s square. If I assume one function as 1 over s square, then we can say this is a frequency shifted version of the function 1 over s square. And there is a shifting in the frequency domain, then there will be multiplication of an exponential function in the time domain by the frequency shifting property. So we can find out the time domain function of f of s by using the frequency shifting property. So moving on to the solution, if we know the inverse Laplace transform of 1 over s square, then we can easily calculate the inverse Laplace transform of 1 over s plus 3 whole square by using the frequency shifting property. And we know the inverse Laplace transform of 1 over s square, right? Yes, the inverse Laplace transform of 1 over s square is t. We studied that the Laplace transform of t is 1 over s square. In that case, the inverse Laplace transform of 1 over s square is t. And now in this case, f of s is equal to 1 over s plus 3 whole square. Now if we compare this function with this particular function, then we can clearly say that this function is a frequency shifted version of 1 over s square. So we can easily calculate the inverse Laplace transform of f of s by using the frequency shifting property. So if we have the shifting in frequency domain, then exponential function is multiplied in the time domain. So we need to multiply e to the power minus 3t in the time domain, because we are shifting this function in the left hand side by a factor of 3. So if plus 3 is here, then we need to multiply e to the power minus 3t in the time domain. And that's why the inverse Laplace transform of 1 over s plus 3 whole square is e to the power minus 3t multiplied with t. And in this way, we have calculated the inverse Laplace transform of f of s. So in this way, we can find out the inverse Laplace transform by the Laplace transform properties. So now we are done with the example number 1, and now we will move on to the example number 2, which is find the inverse Laplace transform of f of s is equal to 2 over s plus 1 multiplied s plus 2. In this case, there are two factors which are multiplied in the denominator, and it is difficult to find out the inverse Laplace transform for this particular fraction. But if we split these two factors as two different fractions, then we can easily calculate the inverse Laplace transform. And we can split these two factors by the use of partial fractions. Before going to the partial fractions, we need to understand two different things: that the partial fractions can be calculated for proper fractions, and in the proper fractions, the degree of denominator is greater than the degree of numerator. In this case, the degree of denominator is 2. If we multiply s with s, then we will have s square, and the highest power of s in this case is 2. And in the numerator, the highest power of s is equal to 0. So we have a proper fraction and we can apply the partial fractions. Moreover, this is the case where the denominator is having real and distinct roots. So this is the first case of partial fractions, and we will discuss some more cases of partial fractions in the next lecture. So moving on to the solution, by the partial fractions we have f of s is equal to 2 over s plus 1 multiplied s plus 2, and now by partial fractions we can split this fraction as a over s plus 1 plus b over s plus 2. By this method we have splitted these factors as two different fractions. Now we need to calculate the value of a and the value of b. Firstly, I will calculate the value of a in the first step, and then in the step number 2 I will calculate the value of b. So in the step number 1, we will multiply this factor s plus 1 on both the sides. So we will have 2 over s plus 2 is equal to a plus s plus 1 multiplied with b over s plus 2. In this way, we have isolated the factor a, and if we put s is equal to minus 1, then this factor will become 0 and we can calculate the value of a. We have a is equal to 2. In this way, we can wisely choose the values of s in order to calculate the values of a and b. So now we have calculated the value of a, and now we will find out the value of b in the step number 2. And in the step number 2, we will multiply the factor s plus 2 on both the sides. So we have 2 over s plus 1 is equal to a multiplied with s plus 2 over s plus 1 plus b. By multiplying with s plus 2 on both the sides, we have isolated the factor b. And now we can calculate the value of b by substituting s is equal to minus 2. And the value of b will be equal to minus 2. So now we have calculated the values of a and b, and now we will substitute these values in this equation, and we will get f of s is equal to 2 over s plus 1 plus minus 2 over s plus 2. This plus is multiplied with minus, so we will have f of s is equal to 2 over s plus 1 minus 2 over s plus 2. And now we can easily calculate the time domain function by applying the inverse Laplace transform in this step. What is the inverse Laplace transform of 1 over s plus a? Yes, it is e to the power minus at, because we have studied the Laplace transform of e to the power minus at. It is 1 over s plus a. So the inverse Laplace transform of 1 over s plus a is e to the power minus at. In this case, we have 1 over s plus 1, so its inverse Laplace transform will be e to the power minus t, because a is replaced with 1. Similarly, 1 over s plus 2 will have an inverse Laplace transform e to the power minus 2t, because a is replaced with 2. And both these fractions are multiplied with 2, so we will have the time domain function as 2 multiplied with e to the power minus t minus 2 multiplied e to the power minus 2t. Here the inverse Laplace transform of 1 over s plus 1 is e to the power minus t, and the inverse Laplace transform of 1 over s plus 2 is e to the power minus 2t. So now we are done with this particular case of partial fraction. We will discuss one more case of partial fraction in the next lecture. Thank you for watching this lecture. I'll end this lecture here. See you in the next one.